Hello everyone, and welcome back to another episode of the Internet Computer Developer Journey. My name is Jessie, and in today's episode we're going to take a deeper dive into canisters in episode 0.4, Introduction to Canisters. In the last episode 0.3, Setting Up the Developer Environment, we downloaded some tools that we'll be using to develop our own canisters on the Internet Computer. And in episode 0.2, Internet Computer Terminology, we went through a couple different phrases and terms that are used to describe the different components of a canister, such as the canister's controller or the canister's identifier. Today, we're going to be talking a bit more in depth about what a canister is and why it's so important to our developer workflow on the Internet Computer. Essentially, canisters are at the very core of doing anything on the Internet Computer development-wise. Whenever you're going to create a project on the Internet Computer, it's going to be comprised of different canisters. So it's very vital that we have a fully comprehensive understanding of what a canister is. So that's why today we're going to dedicate some more time to diving deeper into canisters. So we're going to be using this documentation page, 0.4, Introduction to Canisters. And while there's a lot of great information on this documentation page, I've simplified some of the key concepts into a quick PowerPoint. So that we're going to go through that now just so we can get the core takeaways together. Then if you want to read a little bit more, you can check out the developer documentation, this 0.4 Introduction to Canisters pages, which I highly recommend that you take a look at as well, in addition to this tutorial video. The link to that documentation will be in the description of this video below. So now let's take a moment to do a fully comprehensive introduction into what a canister is. So a lot of the times you may see the Internet Computer canisters referred to as smart contracts on steroids. And that's a great way to describe them since they are both source code and software state. So on other chains like Ethereum, a smart contract is just a piece of code. It does not have a software state that is coupled with the code. That's what makes canisters unique on the Internet Computer, is that they contain both the source code and the software state. So a software state is a persistent record of changes. Changes can be made by making calls to the source code's functions. So if you make a call to a canister's function and the call changes the state of the canister, typically that will be an update call. That change is going to be recorded in state along with all of the other changes that have been made to the canister state since the canister was created. Another unique feature about canisters is that the source code is always compiled into WebAssembly or WASM, and then it's associated with a module of stable memory. Stable memory on the Internet Computer is the Internet Computer's long-term storage. So whenever you have values that you need to be stored long-term, such as persisted across canister upgrades, you're going to want to store them in stable memory. And we're going to dive deeper into stable memory and stable variables in a future module. But for now, it's just important to know that source code is always compiled into WASM and it's always associated with a module of stable memory. It's also important to know that canisters can be written in any language as long as it can be compiled into WASM, and there are several different SDKs and CDKs that can be used to write canister code in different languages and then compiled into WASM. Some of these are Motoko and Rust, which are natively supported by the Internet Computer's IC SDK, or there are also community-contributed CDKs such as the Python CDK and the TypeScript CDK. So to talk a little bit more about canister architecture, we already covered that there are several different languages that can be used to write the source code for your canister. As long as it can be compiled into WASM, it can be written for canister code. So WASM is a low-level instruction format, and it's supported on the IC since it's very portable and it's broadly supported across different platforms. It also abstracts program execution across most modern hardware, making it extremely versatile to run on different nodes across the ecosystem. Another important aspect of canister architecture is an actor. So an actor is an object that processes messages within an isolated state. Actors also enable messages to be handled remotely and asynchronously, which are two important key components to running code on the Internet Computer. Since Motoko is developed specifically for running canister code on the Internet Computer, Motoko natively is an actor-based programming language. When a canister is written, a canister will always include the compiled code for just one actor. A canister cannot contain code for more than one actor. In addition to that code for that single actor, canisters can also include interface descriptions and front-end assets. So canisters aren't restricted to only containing actor code. They can contain other pieces of code like I just mentioned, but they can only contain code for one actor. This next slide contains this familiar graphic from episode 0.2, Internet Computer Terminology, and this is just to review the different canister components and terms that we talked about in that episode. So if you remember, the canister identifier is a globally unique identifier for a canister that can be used to interact and make calls to that canister. And a controller of an individual canister is a principal value that can be a person, an organization, another canister. Principals, if you recall, are not specific to one type of entity. They can be used to identify several different types of entities on the internet computer. Canisters also contain a cycles wallet, which holds the canister's cycles that are used to pay for any resources used by the canister. And then in addition to these three components, we have the smart contract code, which we just chatted about, the different languages that smart contract code can be written in and that it will be compiled into WASM. And then the canister state, which refers to the result of any operation, function call, or transaction that changes the information that's stored within that canister. So now we're going to move on to the different types of canisters. We briefly mentioned these in episode 2 with the internet computer terminology as well, but we're just going to dive a little bit deeper into the definitions of these types of canisters. So backend canisters are the part of the application that does not come in direct contact with the users. It hosts the application's primary source code and functionality, and it typically does not contain user interface assets such as HTML or CSS. When a project is created with DFX, the file structure for a default backend canister is created, and I've included a screenshot of what that looks like in the file system below. There will always be a folder that has the name of the project, so in this example, Hello World, and that is always pre-appended to the word backend, so backend will always follow it using an underscore as the separation character. And within that backend canister, there will always be a default main.mo file. And so this will always be a simple Motoko file that contains a default hello world actor definition that uses a simple method to return a hello world message when the method is called. So next we have front-end canisters. So front-end canisters typically contain the part of the application that's used by users to interact with that application's functionalities. And these are the canisters that typically contain different assets used to create that front-end interface like CSS, HTML, JavaScript, or React. Front-end canisters on the internet computer are also commonly referred to as asset canisters since they hold those front-end assets. When a project is created with DFX, the file structure for the default front-end canister is created using the following format that I've included a screenshot to on the bottom. So in this you can see that it looks similar to the back-end canister where it has a top-level directory that has the name of the project pre-appended to the word front-end with that underscore as the separating character. But the difference here is instead of just containing one file like the back-end canister, the front-end canister by default has two subdirectories, one called assets and one called source. In assets, there are a couple different visual assets like the fav icon, the logo2.svg file, a CSS styling file, and a simple asset text file. And then in the source directory, we have the index.html and the index.js files. So in addition to backend and front-end canisters, there's also kind of a catch-all category that is known as custom canisters. So custom canisters don't fit into the front-end or back-end canister definitions. They might include a mix of both back-end and front-end functionalities, or they might be used for specific functionalities within your application. So for example, if you have a social media application and you have several different components of that social media app, you might have one that handles all of the user's profiles. You might have one that handles all of the messaging within the application, and you might have one that has all of the group activity for the social groups on the platform. You may split these 3 different core functions of the application into 3 different canisters so that they can be referenced by other canisters and help with simplifying management of those individual functionalities. So there might be instances where the profile canister needs to interact with the groups canister, or the messaging canister needs to interact with the groups canister, or different cross canister functionalities like that, where it makes sense to split things for the DApp into different canisters in that manner. And that would be an example of a custom canister setup. In addition to that kind of setup, custom canisters also include the Internet Computer System canisters. So these are canisters that help provide core functionalities for different services on the Internet computer. And a couple instances of those are the Internet Identity canisters, the NNS canisters, and the Management canister. So when you start to develop your application, you may be wondering, should I use a single canister or multiple canisters? If you're developing a simple service-based application and it doesn't have a user interface or any front-end assets, then a single canister might be a good choice, since it's going to include simplified management. It's going to have a simplified canister upgrade process, so whenever you want to make changes to that canister, it's going to be a little bit more simple. And you're also only going to have one set of candid interface descriptions, and we're going to talk a bit more about candid in a future episode. However, if your application is intended to have both front-end and back-end assets and logic, then it might be a good setup to have at least 2 canisters, one to handle the front end and one to handle the back end. This is a pretty standard structure, and this is the default structure that DFX uses whenever it generates a new project. And like I mentioned in the example talking about custom canisters, sometimes it's beneficial to separate different reusable services into their own canisters so they can be imported or called to from other canisters, or even be made available to other developers, such as using the DFX depths functionality, which is a way for canisters to be published and then pulled by other developers into their projects. And we're going to cover DFX depths at length in a future episode, but just make note that that is a possible workflow as well. So canister communication. So we briefly talked about canister communication in episode 0.2, but we're going to dive a little bit deeper into it here. So to recap, canisters communicate with other canisters through the use of asynchronous messages. Each of these messages is executed in isolation because this allows for increased levels of concurrent execution. Messages can also be replies to other messages, or they can just be requests to other canisters and other outgoing external services, such as using HTTPS outcalls. The result of processing a message could be a change to the canister state, a reply message to another canister, or even the creation of another additional canister. If a request requires additional requests to other canisters, such as calling one canister and then that canister in turn needs to make a query call to a third canister, then the first canister may wait for the other canisters to reply first before it returns its response to that message. When talking about canister communication, the term trapping may come up occasionally, and trapping is when a canister fails to reply to a message. So when this happens, the canister state gets rolled back to what it was before that request was made. And remember, canisters can always communicate with external entities like end users or external services. Canisters are not limited to only communicating with other canisters. And another important thing to make sure we have front of mind is that update calls are always used to write changes to the state of the canister, whereas query calls are used to read information from the canister's current state. So earlier in that canister component and terms diagram, we had a canister controller labeled, which was a principal identifier that was labeled as the canister's controller. So let's dive a little bit deeper into what a canister controller is and what it can do. Canisters are managed by controllers. They can have one controller or they can have several controllers. So a canister's controller can be a centralized or decentralized entity. So it can be a single user or a group of users, or a canister's controller can even be another canister. Now, it's also possible that canisters can have no controller at all. And if this is the case, the canister is then an immutable smart contract. Since controllers are responsible for deploying and maintaining the canister, so if a canister doesn't have a controller, it can't be updated or maintained, so that makes it an immutable version of a smart contract. Controllers are the only entity that can perform those types of actions with a canister, so controllers are responsible for updating, deploying, starting and stopping the canister. They're also responsible for changing any of the canister's parameters, adding or removing other controllers, or even deleting the canister. One of the most important workflows for canisters, however, is updating canisters, which is something that controllers can do by submitting a new WASM module to replace the existing module. So when the WASM is updated, the canister's WASM memory is cleared, but the canister's stable memory remains. And that's, if you recall, I mentioned that stable memory is the Internet computer's long-term storage and that it persists across upgrades. And that is a very key functionality of stable memory and canister architecture that we're going to cover at length in a later episode. So lastly, we're going to talk a little bit more about cycles and resource charges. So I've mentioned in a couple previous episodes now about cycles and how important they are since they're used for paying for a canister's resources. And ICP tokens can be converted into cycles, and cycles must be deposited into a canister cycles wallet in order to pay for every operation performed by the canister while it's running on the mainnet. If a canister runs out of cycles and it can't pay for further operations, it will be uninstalled and the code and the state will be deleted. To prevent this from happening, a lot of developers will set what is known as a freezing threshold, which is the ability for the canister to stop accepting requests if the cycles balance dips below a certain point. That way they aren't continuing to burn cycles and are at risk of running out of cycles. So that is something that is very important for developers that have applications live in production to be aware of and know how to set up. And that's something we're going to cover in our module dedicated to managing canisters. So how are these resources charged? So memory usage is charged at regular intervals based on the canister's usage. Computational power, however, is charged at the time that the computation is performed, and there is a limit of how many can be performed per round, and that is something that is an intentional design choice for security purposes. Lastly, we have network bandwidth, and so the cycles for use network bandwidth are charged at the time of usage, just like the computational power is, and the cost is calculated based on the size of the message's payload prior to the message being sent. And there are breakdowns of all of these resource charges with some example figures on the gas cost documentation page to give you an idea of how much different simple operations can cost. So that'll wrap things up for this episode. In the next episode, we're going to have an introduction to languages, where we're going to talk about the attributes of Motoko and Rust. We're going to talk a little bit more about Candid, and we're also going to cover the different community-developed canister development kits, or CDKs. Remember that the documentation page for this episode of the Developer Journey will be linked in the description below, as well as additional resources to different communities such as our Discord community and our developer forum. There will be a specific forum post linked in the description that will bring you to the forum thread for this Developer Journey series, where you can connect with other developers on their developer journey or leave feedback on this series. I'll see everyone next time. Have a good one.